What's the formula for oxalate? Oxalic acid is based on, ic acid is based on oxalate. So what's the formula for oxalate ion? Minus the hydrogens, but the hydrogen is stuck in the middle. Usually for acids, where do we put the hydrogens? At the beginning. So I wouldn't put the hydrogens in the middle. The hydrogens go in the beginning. H2, C2O4. This is based on oxalate. Oxalate ion C2O4 2 minus. That's oxalate. And this is oxalic acid. Adam, did you have it? Did you raise? Oh, no. Okay. What did you get for the formula for oxalate? H2 or C2H2? How did you just memorize that from the book, or where did that come from for oxalic acid? Saw it in the book? Well, when we have oxalate like this, then we have hydrogen oxalate ion, which is HC2O4 minus, and then oxalic acid, which is H2. We don't usually insert the hydrogens in the middle here. Usually, if the hydrogens are written after the carbon, then that implies that the hydrogens are bonded to the carbon. Here, I recognize this as an acid because formula begins with H. So we treat the things differently. So, for example, HC2H3O2 has the hydrogens split up. When I see the hydrogens in the middle here and the hydrogen over here, should I just combine them? C2H4O2. Some people wrote this as a formula for acetic acid. I'm trying to figure out where they got that formula from. Did anybody memorize this formula for acetic acid? C2H4O2? Or have you seen the formula written for acetic acid like this?
I think I've seen it. I just think a lot of people just assume that it would be quote unquote easier to just put the H's together instead of realizing the importance of the H.
Well,
I just memorized acetate and then figured that
acetic
acid is probably
right. People just memorize acetate and then add an H plus. When you add the H plus, you don't really insert it with these ones here because you want to keep it. Do you see acetate in this formula?
Not really.
Not really.
Because there's no indicator that it's...
Right, but I see acetate in this formula. I see hydrogen and I see acetate. So the same thing. If I wrote it like this, C2H2O4, I don't see oxalate there. And so, and it doesn't really look like an acid. It looks something like this. These three hydrogens are what we call non-acidic. This only has one acidic hydrogen. Both these hydrogens are acidic. Oxalic acid is a really important acid in titrations. In Chem 1A, the first titration you do is with oxalic acid. And oxalic acid is what they call a primary standard. It's not just a standard, it's a primary standard. Difference is that a primary standard you can buy in highly pure form. And it's easy to weigh out, it's stable. Usually the primary standard is not what we call anhydrous oxalic acid, it's a white solid. It's the monohydrate. So we get oxalic acid monohydrate, which is a very stable hydrate. And so we use that, and a primary standard should be easy to measure out. Solutions are not easy to measure out. If you have the burette, you have lots of sources of potential error. The initial volume readings could be potential source of error. The final volume reading, another potential source of error. So 2 errors for each measurement because we want the volume. Whereas if you have a solid, you just throw it on the balance. You know, reading a balance is a heck of a lot easier than reading a burette. You know, burette is very tricky to read, right? And so primary standards are usually solids that you can buy in pure form and that are easy to measure out. And so when you do a Chem 1A titration, what you do is you just get some solid oxalic acid. There are lots of solid acids like oxalic acid, ascorbic acid, etc. You just weigh out some oxalic acid, then you know how much you have there, how many moles of acid you have. And then you can figure out how many moles of base that will react with this. In this case, this is diprotic acid. You need 2 moles of sodium hydroxide for every 1 mole of oxalic acid. So it changed the mole ratio there and changed the equation a little bit. This is why I gave you the equation that it gave you. I'm showing, the dimensions. Okay, so I like to write it like this, but oxalic acid is also written like this because here, it's this formula, C2H2O4, this is what we call a molecular formula. The molecular formula doesn't give us much structural information. This formula gives us a little bit more structural information because we don't treat the hydrogens as non-acidic hydrogens bonded to carbon. These hydrogens are acidic hydrogens. Whenever you have acidic hydrogens are bonded to the most blank atom, most electronegative atom. And in that case, it's going to be oxygen. So these hydrogens are actually bonded to the oxygen. There's another way that oxalic acid is written. It's written like this. Or HO2C2O2H. Or I'll just do it like this, CO2H. This formula is called the condensed structural formula. The condensed structural formula is the best because the condensed structural formula will tell you of how things are kind of linked together. But they could be a little bit deceptive how they're linked together. So for example, if I look at the acid chart up on the board over here, the strongest of the weak acids is here. And you see it's oxalic acid. Look how they wrote it up here, HOOCCOOH. And if you have it written like this, then it's pretty easy to figure out the structure. Because the COOH group we see in other compounds as well. So for example, let's look at benzoic acid. Benzoic acid is C6H5COOH. Acetic acid is CH3COOH. And so the condensed structural formula for acetic acid has a COOH group. And whenever we see the COOH group, you know what we call that group? We call that group a carboxylic acid. And so this would be an acid. Yeah. Did somebody get the Lewis structure for oxalic acid?
Maybe.
What did you get?
2 carbons with 1 single bond. Each of them have a double bond to an oxygen.
Okay.
And then they each have a single bond to an oxygen that has a single bond to a hydrogen.
Good. How about lone pairs?
All the oxygens have 2.
All the oxygens have 2. That's it. And so we call this, the trick here is these 2 oxygens aren't actually bonded to one another. And so when we look at the COH group, it goes like this, COOH. Oxygens are separate here. And so this is the carboxylic acid. This is two back-to-back carboxylic acid groups. So this is a really interesting acid, oxalic acid. It has that symmetry. You just cut it in half. You have two COOH groups. So this, you can see that symmetry here. Two COOH groups. With the Lewis structure, it doesn't have to necessarily represent the angles. So for example, if I look at the HOC angle, what is the angle here? It looks like the angle is 180 degrees. Do you see that? But is it 180 degrees? No, it's not. How about the OCC angle? This one looks 90 degrees. But is it 90 degrees? No. And for Lewis structures, we don't care. You know, the angle doesn't have to be correct. We don't care. But when we draw a wedge dash diagram, we need to care what that is. In order to do a wedge dash diagram, we follow the sequence. What is the sequence? The first thing we look at is how many groups. If there are two groups, what's the geometry, electron geometry? If there are two groups, the electron geometry is linear, correct. If there are three groups, the electron geometry is trigonal planar. And if there are four groups, the electron geometry is tetrahedral. So let's stop. We don't look at hydrogen because it's terminal. We don't look at these oxygens because those are terminal or this hydrogen. We look at what are called bridging or central atoms, like this oxygen. How many groups of electrons around this central? 4. A lone pair, that's 1. Another lone pair, that's 2. A single bond, that's 3. And another single bond, that's 4. That's 4 groups. 4 groups adopts what? Electron geometry? Tetrahedral. So the electron geometry of this oxygen is tetrahedral. And so I'll try to draw that out. Tetrahedral, I'm going to try to draw the same way each time, or close to it, or something similar. And so this one, let's see, how will I draw this? So I draw oxygen-hydrogen bond in the plane of the page. Do you recognize this? This is 4 groups, 4 single bonds. In order to get the 4 groups as far apart as possible, we need to spread the groups at what angle? 109.5. And so this is tetrahedral. And so what I'm going to do is I'm going to put this hydrogen up here and this carbon down here. And that means one of these groups sticks out. This group will be the lone pair, which wedges out. And this group that sticks in will be the lone pair dashed here. Do you see that? And so one lone pair comes out, the other lone pair goes in. The hydrogen's in the plane, the carbon's in the plane. This. Although it's a tetrahedral electron geometry, and the angle is set at 109.5 ideal, what is its molecular geometry? The molecular geometry, the electron pairs we don't pinpoint, but we can pinpoint the atoms. And when you see the atoms, what geometry or shape are the atoms in?
Trigonometry? No.
What is it? It's it's not trigonal. Did you say trigonal pyramidal?
I was going to, but then I looked at my notes and said no.
Yeah, okay. That's trigonal pyramidal.
Would it still be tetrahedral?
It wouldn't be tetrahedral because the atoms don't follow the same shape.
Okay.
It's bent, yeah. And the ideal angle, it's bent at what ideal angle? This we say bent at 109 or 109.5. But there are going to be distortions. The reason they're going to be distortions is because the lone pairs take up more space than a bonding pair. And so each lone pair distorts the bond about 2 degrees. We have 2 lone pairs, so the total distortion should be about 4 degrees. And so what do you think the HOC angle is? 105. And so the HOC angle, this is bent. Okay, so the electron geometry we got is tetrahedral. And tetrahedral angle is 109.5 degrees. But the molecular geometry, the MG, is bent, and the ideal angle is 109.5, but we're going to expect a distorted angle of about 105 degrees.
How did we come up with 105 instead of the 109?
Instead of the 109, because the lone pair takes up more space. Because the electrons in a bond are pulled between 2 atoms, but a lone pair is just pulled onto 1 atom. And this lone pair is going to push these bonding pairs in a little bit. In fact, I'm going to have 2 lone pairs. And 2 lone pairs take up more space here and here. They take up more space, they need more room, so it's going to push these 2 in to create more room for these big lone pairs here. Does that make sense? And so this is going to be distorted because of the 2 lone pairs here. Now, 1 lone pair is sticking out here, the other is going in. All right, now there are different ways of drawing tetrahedral. This is one way here. In plane, wedge dash. So what's next? This carbon, which is going to have a double bond to another carbon here. So let's look at this second atom here. How many groups of electrons around carbon? 4 pairs. There are 4 pairs. But one of these groups has 2 pairs, and you can't split them apart. And so double bond is considered as 1 group, not 2 separate groups. And so there are not 4 groups here, there are 3 groups. If there are 3 groups, then that means it's 3 groups is, electron geometry is going to be trigonal planar. Which sets an ideal angle of 120 degrees. What is the molecular geometry? Also trigonal planar. And the ideal angle would be 120 degrees, but we expect some distortion. We expect some distortion because a double bond takes up more space than a single bond. So here I have something like that. This Not exactly. And so this is a trigonal planar arrangement. Here I have a double bond. I have two single bonds. And so the double bond is going to take up more space. If a double bond takes more space, it's going to push the two single bonds in closer to one another. The double bond is going to require more breathing room. And so if that's the case, then the OCC angle, you see that? OCC angle should be what? Let's take a look. The OCC angle should be, well, it's kind of widened out a little bit. And so this is going to be about a 2 degree distortion bigger. And then the OCO angle would be what? The OCO angle should be about 120 degrees, 22 degrees. And then the OCC angle, this would be the double bond O here. This would be the single bonded O. Should be about 116 degrees. So this one widens out to 122. This one widens out to 122. All these angles have to add up to 360 because they're in a plane. And so this has got to go down to 116. Do you see the angles there? Okay, this carbon is going to be the same as this carbon over here. And then we have an oxygen, which is going to be the same as oxygen here. And the hydrogen. Now, how we draw it depends on, where we twist, or how we twist the molecule. If I have single bonds like this, single bonds, they have something called free rotation. And so what happens is, if I'm looking at this whole thing can rotate. This thing can flop around and rotate. So what I'm going to do is I'm just going to flatten it in the page and then draw it. So single bonds, they're free to rotate, so I can twist this. And this whole thing can rotate around like this. So if this whole thing can rotate around, what I want to do is I just want to rotate it so I can get as many bonds in the plane of the page as possible. Double bonds don't rotate though. And so I can't do the same with double bonds. But single bonds do rotate. And so I can rotate this. And they're rotating. And so this part, this COH, the OH is like a propeller. It can rotate in and out of the plane if it's spinning. And so I'll just keep it flat. The symmetry of this, it should be fairly symmetrical. In fact, I might have drawn it like this on this side too, less keen. And so it boils down to how you draw tetrahedral. So let's take a look at drawing tetrahedral structures. Do you see this, the way it's drawn here? This is pretty much the standard way it's drawn. There are two angles that we look at in a tetrahedral structure. So what I do is I orient it. So this bond is in the plane, this bond's in the plane. So one bond wedges out, the other one's dashed in. And so it depends on the angle you look at it. If I look at it from above, then the wedged out one is to the right and the dashed in one is to the left. And so let's keep this in the plane. If you look at it from above, the wedged out one is to the right of the dashed in one. If you look at it from below, then that changes the perspective. If you look at it from below and from this side, the wedged one is to the left of the dashed one. And so this is the standard way we draw. And we should always draw it like this if we're just drawing a tetrahedral molecule here. This is the standard way we draw it, except for molecular geometry drawings or wedge dash, the book doesn't put lone pairs. I want you to put the lone pairs on here. But again, here, take a look at the relative position. The wedge is to the right of the dash. And you're kind of looking down on this tetrahedral there. I don't like this one. What's different?
That the one of the lines, I think it's supposed to represent the back line. It's dashed, but it's a wedge.
Yeah. There's a lone pair here that they didn't put on nitrogen. This is also tetrahedral electron geometry. We have the lone pair sticking up, which you don't see there, and then we have the rest. And so this is looking at it from underneath here. You see, if we look at it from underneath, then the wedge is to the left of the dash. Can you see that? And so we're looking at it from a different perspective. What we need to do is we need to look at it from the same perspective each time. So I'd like you to draw it the same way. Yeah. Let's see here.
Do you know if the kids at the bookstore are able to do double bonds? I know they have like the little.
Those, you're going to organic chemistry. You need a kit, and you'll just buy the kit. They're worth buying for general chemistry too. It's just that a lot of people don't go into organic chemistry, and so they don't bother buying the kit, and it's kind of an investment. Although, you know, that they have it at the bookstore, but they also have it on Amazon too. I bought a kit recently. It wasn't that expensive on Amazon. I don't know, how much is the bookstore selling it for?
It's like in the teens, but it's not 20, it's like 16.
Oh, then yeah, that's worth it.
Because I was going to get it.
You should get it. I recommend it. We're going to use it so you can see with the kid, you know, if it's worth getting or not. Yeah, but I highly recommend a kit because then you can see what looks weird and what doesn't look weird on paper. Hopefully this stays on here. Did you want to see tetrahedral and pass it around? There's another way that we orient it. Let me talk about this other way that it's oriented next. And that is when we have chains of tetrahedral atoms connected to each other like this. Here's a single tetrahedral. Single tetrahedral we'll just draw like we normally do. This should look more symmetrical in the way I've drawn it. It's all right. So when we have one tetrahedral molecule like methane, we draw it like this. These two single bonds are in the plane, and then one single bond is going to wedge out, and then the other will dash in. The perspective is looking down on this from the right. And so the wedge is to the right of the dash. When we have a chain, like for example in butane or these types of things, there are different ways we can start this. But when we have a chain, we usually do this kind of zigzag style arrangement. And so these are all tetrahedral. So in organic chemistry, but means 4 carbons. And so we have a 4-carbon chain. When we do a 4-carbon chain, we just do a zigzag chain like this. So here's a carbon, zigzag, zigzag. The reason we do a zigzag chain like this is so that we can draw in a straight line. Because, as you recall, there's free rotation about the single bonds. So I could rotate this so it doesn't zigzag in a straight line. It'll start to kink. And so if I rotate this down, then the structure continues straight down, or can go backwards, back over there. This is like a big spaghetti noodle. So what I want to do is I just want to lay it flat like this in a horizontal arrangement. But this whole thing's twisting at room temperature. And so I just need to take a snapshot of it here. And what I try to do is get as many bonds in the plane of the paper as possible. And so over here I have a hydrogen-carbon bond in the plane, carbon-carbon bond, and then carbon-hydrogen bond in the plane. Now all these are tetrahedral, so if I have 2 in the plane, then 1 is going to wedge out. And I want to pick it the same way each time. So for example, this one I'll have wedged out like this, and this one I'll have dashed in like this. And so this is a tetrahedral that's kind of tilted. No. I got. Okay. Do you see that here? Okay, so then what I want to do is if I have the wedge to the right, the dash to the left, I'm going to have it the same way each time. So the wedge to the right, the dash to the left. Wedge to the right, dash to the left. So do you see the tetrahedral carbons there? All right, so this is a zigzag chain. So this is the other way we draw tetrahedral. So you can kind of see here, we're doing zig, zag, zig. And so we put these zig in the plane, zag in the plane, zig in the plane. These are all in the plane. If those are all in the plane, then the wedge to the right, dash to the left. You see here? The same thing here. This will be zig, zag, zig, zag. And so I'm going to put all those in the plane. Although this can rotate out of the plane, if I just rotate this. This CH3, we call this a methyl. It's methane. 1 carbon means methyl. And if it's a CH3, we call it methyl. So this is 2 CH3s. These are 2 methyl groups connected. This is 2 methyl groups on the end, 1 CH2 group in the middle. The CH2 group is called methylene. This is propane. Again, it goes zigzag, zigzag, and we put those in the plane, wedge out, dash in, wedge out, dash in, wedge out, dash in. Butane, we go zigzag, zigzag, zig. Put those all in the plane, and then wedge, dash, wedge, dash, wedge, dash, wedge, dash. See, so there's certain ways we draw these things. Now, what screws things up, for example, if I'm not consistent here, then it confuses people. So if I have it like this, and then all of a sudden I change the perspective, then that looks weird. Do you see that? This just looks weird. It would be kind of a weird, distorted structure. Because on the one hand, you're looking at these carbons this way, and then looking at this one in a different orientation. And so somebody who's experienced, somebody who has model kits and who looks or tries to visualize these things in 3 dimensions will go, that doesn't look right. It doesn't look right. The same thing like this. I see this kind of stuff all the time. If I did that, this is just a weird structure. Doesn't really correspond to anything. This would be really distorted tetrahedron. Can you see? And that would be something like this. I have the zigzag here in the plane. And then depends on which perspective. Do you tilt it this way or do you tilt it this way? That's going to determine, if you tilt it this way, wedge is on the left, dash is on the right. If you tilt it this way, then wedge is on the right, dash is on the left. If you don't tilt it, then they superimpose and you can't see the wedge and the dash. So we have to tilt it a little bit so you get that perspective. But in this case, if I tilt it this way, then that means I have one dashed in here, and then I have to have another, not wedged down, but I have to have another that's wedged up. So you have a structure that looks like this. Well, does that look tetrahedral to you? Or does that look like some kind of mutant structure? This looks like a mutant structure. And so if somebody saw this, they go, wow, that's a mutant structure. You clearly don't know structure if you draw something like this. But people draw something like this all the time because probably lack of experience with models, maybe. And so there is a way that we draw it, and otherwise it looks strange. Okay, I'm going to skip polar heritage molecules temporarily, and we'll come back to that. So let's look at the structure of organic compounds next. This is optional, but we'll cover it. Organic chemistry is the chemistry of carbon compounds. There are lots of carbon compounds. Because carbon doesn't mind bonding to itself. Oxygen doesn't really like to bond to itself. A lot of other elements don't like to form these long zigzag chains. Because it can form these zigzag chains. You don't always have to zigzag, they can zag, and it tweaks the structure. It doesn't really matter. But we get these chains. These chains can grow very long. Usually people memorize it to 10 carbons. Like, for example, meth. Meth means how many carbons? 1. Eth means 2 carbons. Pro, 3 bute, 4 pent, 5 hex, hept, oct, none, deca, dec, 10. But these molecules can grow way bigger than 10. So what's 11? What's 20? What's 22? I used to know 22 molecules because I was working with a molecule that had a zigzag chain of 22 carbon atoms. I think it was like ICOS, I actually forgot. I rarely use it. But when we have just carbon and hydrogen, these are called hydrocarbons. And hydrocarbons have some interesting features. Carbon-hydrogen bonds are nonpolar. And so when we have nonpolar bonds, it forms nonpolar molecules. Nonpolar molecules are like oil. Oil and water don't mix, and so these don't mix with water. Water is very polar. And we have certain kinds of hydrocarbons. We have hydrocarbons that are the alkanes, the anes, the A-N-E. Then we have the alkenes, the E-N-E ending. Then we have alkynes with the Y-N-E ending. Alkanes all have single bonds. Alkenes will have a double bond thrown in there. Alkynes will have a triple bond thrown in there. But all you need to know are some simple things. These hydrocarbons are all flammable. They're all electron rich. So if we look at something like pentane, there's different ways we can represent the formula. Actually, we'll look at butane. Look at butane there. Bute is 4 carbons. So it's C4. And then how many hydrogens we have? We can count them up. It's 3 plus 2 plus 2 plus 3. 10 hydrogens. And so C4H10. But there's a problem. If we have C4H10, we could have branches. They don't have to be zigzag chains. We could have zigzag chains with branches. And so the problem with butane is we could have a zigzag chain like this, 4 carbon atoms. But we can also have a zigzag chain with 1 additional carbon attached to, let's say, the middle one here. Both of these are C4H10. But there are 2 different structures for C4H10. So if you're given C4H10, how do you name it? You can't name this. You can't name this because we don't know which structure it is. Is it a simple chain of 4 carbon atoms, or is it a chain of 3 carbon atoms with 1 carbon atom stuck on the middle? We don't know if it's butane or isobutane. Those are the names for those 2 structures. And so this is isomers. And so it could be butane, or it could be isobutane. Which one is it? Butane and isobutane have different boiling points. They have different properties. Slightly, they have some similar properties because they both burn. And so there's not enough information. And therefore, we like to use something called the condensed structural formula. The condensed structural formula for butane is CH3. That's the first carbon. If you look at the first carbon, how many hydrogens do we have bonded to it? 3 hydrogens. This carbon bonded to 3 hydrogens, we call this a methyl group. A methyl. And then a CH2, a carbon with two hydrogens bonded to it. This is called a methylene group. And then another CH2 followed by another CH3 group, which is methyl. Pentane would have a methyl and then three methylenes and then one methyl. Methyls are usually at the ends, and methylenes are in the middle. Isobutane has a different structure. We have a methyl group here, and then the second carbon here has two methyl groups actually attached to it. One hydrogen, then is CH3. So it looks something like this. So this is like a propane chain with a methyl group stuck in the middle. Or this group here. This is like a fishtail group. This group here is called the iso, which has a fishtail here. And so isobutane has this little fishtail structure here. If we go to C5H12, there are three isomers for. So C5H12 has three isomers. Isomers are the same formula, different structure. Isotopes are the same element, but with different masses or different number of neutrons. And so we have the three isomers of C5H12 would be pentane. This is N stands for normal. This is normal pentane. Zigzag, zigzag, zigzag. A chain of 5 carbon atoms here. And then we fill all the remaining positions with hydrogen. Isopentane has a little fishtail group. So we have this CH3, CH3, 2 CH3s stuck to this carbon. That forms a fishtail here. And there are a total of 5 carbons in this structure. So this is isopentane. This is neopentane. Neopentane has this tetrahedral carbon in the middle with 4 methyl groups bonded to it. So neopentane would look like methane here, except rather than having hydrogens here, you have methyl, that is CH3, 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 CH3. And neopentane has a spherical symmetry. It looks like a ball, you know. And in fact, methane kind of looks like a ball too. It's spherical, asymmetric. So in organic chemistry, you're given a formula like this, a molecular formula, and then you try to figure out how many different isomers are there that you could draw for that particular formula. And the isomers are going to come from just different ways of linking these things together. And bonding it. Okay, so that's just a brief introduction to hydrocarbons. You don't need to know much about that. Just general knowledge for these. Alcohols and ethers, that's another one. Alcohols are significant. So if we look at water and we remove the hydrogen and then attach a group, this group is called an ethyl group. Ethyl because it has 2 carbons. Methyl has 1 carbon. Methylene is this thing in the middle. So an ethyl group consists of a methyl group and a methylene put together to make a 2-carbon group. Call it a substituent. And so if we remove that hydrogen and then just tack on ethyl group there, then we form ethyl alcohol as an ethyl group, and this is an alcohol group here. An alcohol is a COH group, or ethanol. This is the molecular formula, but if we have the molecular formula for this, there are isomers. So if you're just looking at C2H6O, it could be ethanol, or ethyl alcohol, or C2H6O could also be this. This is a different structure, but it has the exact same molecular formula. However, if we do a partial condensed structural formula, this is a partial condensed structural formula. And so when we look at ethanol, there are different ways we can write the formula for ethanol. The least descriptive way and the most ambiguous way is just like this C2H6O. A better way of doing it is C2H5. C2H5 is an ethyl group, OH. This is the alcohol. So this is ethyl alcohol. Or the best way is the condensed structural, CH3, CH2OH. So there's a methyl group, methylene group, and then the alcohol, which is the COH. So methyl group, methylene group, and then the alcohol. Okay. The way we draw it is, we try to draw it like this. Just doing it. We just try to do a zigzag thing, try to get as many atoms in the plane as possible. So if that's the case, then this first carbon's tetrahedral. And a wedge dash. This second carbon's tetrahedral. We should have a wedge and a dash. This oxygen, what's the, they're 2 lone pairs. And so what's the number of groups around the oxygen? Looking at the Lewis structure. This oxygen has how many groups? Single bond 1, single bond 2, lone pair 3, lone pair 4. 4 groups total. 4 groups means it's tetrahedral. And therefore, I'm going to have a wedge lone pair out and a dash lone pair in. Okay, do you see that here? This structure? And so this would be my methyl, CH3, my methylene, CH2, and my alcohol, OH. So CH3, CH2, OH. However, this formula, the molecular formula, could also be dimethyl ether. And so if we remove both the hydrogens and replace them with methyl groups, this is what we get. And so dimethyl, we have 2 methyl groups attached to this oxygen. So the COC linkage is called ether. And so we have 2 methyls, that's dimethyl ether. You don't need to know organic nomenclature. For dimethyl ether, we could try to draw this in the wedge dash diagram, like this. I drew it down, they drew it up, but it doesn't really matter. So they want hydrogen down to carbon, up to oxygen, down to carbon, up to hydrogen. So this is their zigzag pattern here. Then we'll complete it. Okay, so ethers are going to be a COC linkage. Alcohols are going to be a COH linkage, like this. So methanol is this, it's a one carbon alcohol. This is also called methyl alcohol because we have a methyl group attached to the alcohol. So methyl alcohol. The alcohol group is called the hydroxyl. The hydroxyl group is this is OH. The alcohol would be COH linkage. So this is methanol. This is butanol. It's a 4 carbons in a zigzag chain with alcohol. Now, hydrocarbons are non-polar, but alcohols are very polar. Alcohols are very polar because this is a very polar bond. Oxygen, hydrogen, there's a big difference in electronegativity. It's not ionic. It would be a polar covalent bond. Very polar. And so methanol is, in a lot of ways, it's like water. And so methanol and water like each other. Ethanol, if you look at the hydrocarbon part of ethanol, it's getting bigger because now we have an ethyl group rather than an methyl group. Ethyl group's bigger. And so this is being less water-like, but still ethanol loves water. Does butanol love water? Butanol doesn't really like water. Butanol doesn't like water because look at this chain here. This hydrocarbon chain is nonpolar. The bigger the hydrocarbon group becomes, the more oil-like it is, and the less water-like. Although this group, the hydroxyl, having this group over here is still very polar, but we have this huge nonpolar part of the molecule, which means it's becoming more and more oil-like, less and less water-like. And so this is butanol or butyl alcohol. The butyl group would be a CH3, CH2, CH2, CH2. This is methanol. Okay. This is 3 carbons. 3 carbons pro, and this forms a fishtail. You have 2 methyl groups attached to that carbon. That's like a fishtail here. So this is called isopropyl alcohol, or rubbing alcohol. Methanol and isopropyl alcohol you don't want to drink. Methanol can cause permanent blindness or death. And isopropyl alcohol, I'm sure you can die from drinking that as well. You can die from drinking ethanol too, but at a much larger quantity. This ethylene glycol is 2 alcohols. You see the COH here and the COH here. It's kind of symmetric. You see how they did the zigzag there? They did that to draw as many atoms in the plane. Okay, so zigzag, zigzag, and then wedge, dash, wedge, dash. This is bent. There are 2 lone pairs here that they aren't showing. There's 1 lone pair wedged out and 1 lone pair dashed in. 1 lone pair wedged out, 1 lone pair dashed in. I'd like you to draw the lone pairs in the wedge dash diagram as well. Ethylene glycol is very water-like. This stuff, you can mix it easily with water. When I look at this has a COC linkage. COC linkage is neither. And this is called diethyl ether because we have an ethyl group here and another ethyl. So we have 2 ethyl groups attached to this. This is diethyl ether. Here they're doing the zigzag, but it's a little offset. This one, the perspective is looking at underneath. Like looking at it from underneath this, rather than looking at it from the side. Do you see that? And so these are two wedges that are coming out. So I got two wedges coming out, a dash going in, and then this could be in the plane. Actually, no, this is going to be wedged in. We got two dashed in, two wedged out. And so the perspective on this is a little bit screwed up. This is not how you draw it. We draw it differently. This is methylphenyl ether. This is another ether. And we see the CO seedling. CH3 is called methyl, and this is called a phenyl. A phenyl is like a benzene ring, where you knock one hydrogen off and replace it with something else. So it's a phenyl. Constituent. Do you know if you drink methanol, the methanol in your body gets converted into this acid. So the methanol in your body gets oxidized to this. This is called the carboxylic acid. And carboxylic acid is going to have a COOH. This is the simplest carboxylic acid with one carbon, so it's called methanoic acid. Methanoic acid has one carbon and a COOH. Nobody calls it methanoic acid. Do you know what everybody calls it? Formic acid. So if you were to drink methanol, your body oxidizes the methanol to formic acid. And then the formic acid attacks your optic nerves irreversibly. So it can cause permanent blindness. Whereas if you drink ethanol, you know, the ethanol in your body can get oxidized to, what's this acid here? This acid is acetic acid or ethanoic acid. Ethanoic acid has two carbons, so acetic acid. Acetic acid we can write as a condensed structural formula. So the condensed structural formula for acetic acid is CH3COOH. The condensed structural formula for formic acid would be CHOOH. Or that. This is called propanoic acid, which doesn't have a common name. But if you drink ethanol, it gets converted into acetic acid in your body. That doesn't just happen in the body. You know, ethanol is easy to oxidize. So, let me tell you. About a story about ethanol oxidation. You know, we can have complete combustion, that's complete oxidation. If you were to completely oxidize ethanol, do you know what it forms? Or you completely burn ethanol? It forms carbon dioxide, yeah, CO2. In fact, all these a lot of these organics are highly flammable. So ethanol is flammable, ethane is flammable, methane is flammable, propane is flammable, butane. And when you burn these, they all form CO2 and water. But you don't have to completely oxidize it, you can partially. So for example, incomplete combustion of methane or methanol or butanol or ethanol. Incomplete combustion can make soot, you know, which is carbon and carbon monoxide and other things. But those aren't the only products that you can have. That's incomplete combustion. We can have incomplete oxidation. So this is my story that happened to me, true story. As I went camping in Joshua Tree, and so I stopped by think I stopped by the dollar store on my way out there, pick up some supplies. This was in Yucca Valley, which is near Joshua Tree. And while I was in the store, they had a $1 bottle of wine, and it was Santa Barbara wine. So I thought, wow, Santa Barbara wine, $1 bottle. I'm going to buy some. So I bought a bottle of this to enjoy by the campfire. But when I opened it and drank some of it, it was awful. I had to spit it out. You know what it tasted like? Tasted like
Alcohol, like isopropyl alcohol.
no. Ethanol has a kind of a sweet taste. I don't know what isopropyl alcohol tastes like. I've never tasted it, but maybe it tastes like that. And methanol, I've never tasted that either. But ethanol, I've tasted, and I don't mind the taste and smell of ethanol. That's why it's hand sanitizer. You know, the methanol hand sanitizer. Stay away from methanol. The FDA issued an alert. You know that some hand sanitizers are contaminated with high levels of methanol. So you don't want to use those. They have a list of manufacturers don't buy hand sanitizer from. They got lots of methanol in there. But it tasted like vinegar. You know what vinegar is made out of? This is part 2 of the titration lab. Part 1 of the titration lab was to use the HCl to determine the molarity of the sodium hydroxide. Part 2 of the lab is once we know the molarity of the sodium hydroxide, we're going to use that sodium hydroxide to determine the molarity of vinegar. Vinegar is an acetic acid water mixture. And so we're going to use it to determine the molarity of acetic acid and the percent by mass composition, which we didn't do, but we're not going to do part 2. And so what I figured was this. I figured that, you know, the wine bottle, there's a cork here. And what must have happened is some air must have gotten through the cork here. And air has oxygen, so some oxygen must have leaked through there. And what that did was it didn't completely oxidize it. And so the ethanol in the wine was partially oxidized. In organic chemistry, we use this to indicate oxidation. So this is some oxidizer. So we're going to oxidize that. And this gets oxidized to, well, there's some steps here, but it gets oxidized to this. Oxidation is losing electrons. When we're dealing with redox chemistry, we look at oxidation state. So Lewis structures don't have to show the three-dimensional part of it, but there are 3 ways of counting electrons in an atom. 3 ways of counting electrons is 1, the octet. This one. And the second way of counting electrons is formal charge. So formal charge, what do we do with the bonds? Do we count all the electrons in the bonds? No. We count half of them for each atom. So we split the bonds in half. And so for formal charge, it looks kind of like this, splitting up the electrons. Lone pairs belong entirely to that atom. We don't have to split those up. But this is how we split up the electrons using formal charge. So octet, we're kind of double counting things. Formal charge, we don't double count. That's formal charge. And so we split up this structure like that. Oxidation state's different. Oxidation state is winner take all. Who's the winner? The winner is the more electronegative. So hydrogen versus carbon, which one is more electronegative? Carbon. So carbon takes all the electrons away from hydrogen. Carbon versus carbon, who's the winner? Yeah, carbon versus carbon is going to result in a tie. And so they'll have to split. There's going to be a tie. Carbon versus hydrogen, carbon wins. Carbon versus oxygen, who wins? Oxygen wins. Oxygen versus hydrogen, who wins? Oxygen. So if we look at the formal charges in ethanol, all the formal charges are 0. However, if we look at the oxidation states in ethanol, the oxidation states aren't all 0. And so hydrogen ends up with no electrons, so hydrogen gets +1 oxidation state. But if we look at the oxidation state for this first carbon, carbon has how many valence electrons? 4 valence. Minus how many does it end up in the structure with? So if I count it, the greens is 2, 4, 6, 7. This gives us -3. So the oxidation state of the first carbon is -3. This diagram is probably getting hard to look at. Can you see what the second carbon's oxidation state is? So the second carbon has a valence of 4, minus how many electrons does it have in the count? It's going to have 2, 4, and then 5 from this, and none from this. So it's going to have 5, which gives us a -1. So the oxidation state of the second carbon is -1. The oxidation state of this oxygen is, oxygen normally has 6, and it has 2, 4, 6, 8 in this. And so its oxidation state is -2. So rather than doing this, these are, the 3 ways of counting. Actually, there's more. These are the 3 main ways of counting electrons in a structure. 3 ways to count electrons in a Lewis structure. The first way is by octet. What's the total number of electrons surrounding it? And so I circled that in blue. The second way is formal charge. Formal charge is this. We assume the bonds are 100% covalent. Assume 100% covalent bonds. What that means is, regardless of electronegativities, everybody's going to share equally. So we know oxygen is much more electronegative than carbon, but in formal charge, they split in half. Hence the red splits the bond in half. And so it's 50-50 sharing of bonding electrons. 50-50 sharing of bonding electrons. The third way to count is by oxidation state. Oxidation state assumes the bonds, this is heteroatomic bonds. Hetero means 2 different atoms or 2 different elements. Assumes hetero bonds are 100% ionic. If that's the case, then it's winner take all. So when we go to acetic acid, we're just going to look at oxidation state. Now this is a Lewis structure. Lewis structure doesn't have to be accurate three-dimensionally. Okay, so winner take all, oxidation state. Carbon versus hydrogen, who wins?
Carbon.
So it's just taking 6 electrons there. Did you see that? It's taking 6, 2, 4, 6. Carbon normally has how many? 4. But carbon versus carbon, who wins?
Yes.
It's going to be a tie, and so nothing we can do here. And so if it's a tie, they're going to split it 50-50, which means in addition to 6, I'm going to add 1 more from the carbon-carbon bond. So that's going to be 4 minus 2, 4, 6, 7. 4 minus 7, that's equal to minus 3. And so the oxidation state is minus 3 for that carbon there. Did the oxidation state change on the methyl group? No, it didn't. Methyls are electron rich. Minus 3 is pretty electron rich. Okay, let's go to this next carbon. If we look at the second carbon, carbon versus carbon, it's going to result in a tie. Carbon versus oxygen, who wins?
Oxygen.
Oxygen wins. And so how many electrons does the second carbon end up with? Well, it's going to end up with 1 electron from the split with carbon, and then 0 and 0. And so this only ends up with 1 electron. So it's going to be 4 minus 1, which is equal to plus 3. So the oxidation state of the second carbon is plus 3. Well, what happened? It went from minus 1 to plus 3. As the oxidation state goes from minus 1 to plus 3, how many electrons were lost? So if you go from minus 1 to plus 3, how many negative charges did you lose? You lost 4. So it lost 4 electrons. So this is why we say it's oxidized, because ethanol becomes oxidized here. Now the oxygens are going to be minus 2, because oxygen's going to take all the electrons. It's 2, 4, 6, 8. So that's 8 minus 6. Or no, sorry, 6 minus 8. It's normal versus what it has. 6 minus 8 is minus 2. The same thing with this one. This is going to be 6 minus 8. This is equal to minus 2. Well, so nothing happened to the oxygen. So what happened was to the second carbon lost electrons. So what happened here with the wine is that some oxygen got in and partially oxidized the ethanol to acetic acid. One of the properties of acetic acid, all acetic acids taste sour. And so, in general, acids taste sour. And so that's what happened to that. And so this went from wine to vinegar. To prevent this from happening, you know what they add to wine to prevent it from being oxidized to vinegar? What's added to wine to prevent it from being oxidized are antioxidants. Do you know what the most common antioxidant they add to wine is? Sulfite. What's the formula for sulfite? SO3 2 minus. Well, if it's an antioxidant, then that must mean there's got to be something that's electron rich. Because the way that the antioxidants work is that oxygen will attack the antioxidant before it attacks the ethanol. So the antioxidant has to be easier to oxidize than ethanol. And so the oxygen gets in here, what does it attack? Well, it's not going to attack the oxidants, it'll attack the sulfur. What's the oxidation state on sulfur in sulfite? So oxygen's -2. This is the other way we do. There are two ways we do oxidation state. One, we do it structurally. Two, we do it using the rules. So if oxygen's -2, we have three of those. So it's 3 times -2 is -6. -6 plus 1 gives us -2. So sulfur must be +4. Well, +4 is already quite positive, but that's not the max. What's the maximum positive charge on sulfur? +6. +6 is correct. So sulfur has a chance to lose 2 more electrons. And so this is it. And so sulfide can be easily oxidized to sulfate. I don't know what sulfide tastes like. But you know, they put this in wine. Actually, they don't put this in wine. Do you know what they put in wine? It says it contains sulfite, but then they, rather than putting sulfite, because if you put sulfite, you have to put a salt. Like if you put sodium sulfide in, you know what sodium tastes like? Sodium ions? They taste salty. So if you put sodium sulfite, it's going to make your wine taste salty. Do you want salty wine? No.
I mean, maybe it'll go well with the crackers.
Yeah, I'll probably go with the crackers, so you can buy unsalted crackers and then just drink the salted wine. What about potassium sulfite? Potassium sulfite is going to taste salty too. This is going to have a different salty taste, like sea salty taste. Lithium? Lithium's getting expensive, you know, because they use it in batteries. But before being heavily used in batteries, and it's still being used in antidepressants. And so lithium sulfide might be good because it could be like an uplifting to your mood or something like that. Yeah.
That's what it does.
Yeah. So lithium sulfide. But anyway, probably don't want to use a salt because salts tend to make things taste salty. So instead of using a salt or an ionic compound, they use this. It's not sulfite that they add sulfur dioxide gas. So they'll bubble some sulfur dioxide gas and it'll dissolve some sulfur dioxide gas in the wine. But how can they call sulfur dioxide sulfite? And why don't they just call it sulfur dioxide? Well, if you look at sulfur dioxide is a poisonous gas, right? At higher concentrations. So we don't want that necessarily, yes. But it's going to have the same redox properties. Why does sulfur dioxide have the same redox properties as sulfite? What's the oxidation state of oxygen in sulfur dioxide? -2. And the oxidation state on sulfur is
4 up to 6.
+4. And so it's going to have, you know, pretty much the same redox properties. And sulfite maybe sounds a lot better than sulfur dioxide. I think so. You can see something like this. There's a lot of talk about sulfites in wine. Is it safe, etc. And so here they say, okay, what are sulfites? This is the truth about sulfites in wine, February 4th. Sulfite is another word for sulfur dioxide. It's also antioxidant and antibacterial that helps keep wine fresh. So what that means is when the oxygen leaks in here, it attacks this. And converts that fully to sulfur dioxide or some other, like sulfate or something like that, rather than attack the ethanol. And so this is used as a sacrificial reducing agent. Okay. The problem with that Santa Barbara wine is they needed to add a lot more sulfur dioxide. You know, if they had a lot more sulfur dioxide, then it should have been okay. But what happened was that all the sulfur dioxide got eaten away by the oxygen and then it attacked the ethanol. Or, you know, the other thing is if this oxidized completely. You know what complete oxidation of ethanol gives? Not carbon, but carbon dioxide. complete oxidation of ethanol gives us carbon dioxide. And so if my wine, I mean, maybe they had too much, if there was no sulfur dioxide in there, and if they give it plenty of time, eventually I'm going to get sparkling wine or just sparkling grape juice because there's no ethanol in there. So if I get sparkling grape juice, that would have been fine. Because then the ethanol would have been converted into CO2, and then I just have sparkling grape juice, which I would have drank it. But instead, I didn't drink it, and you know what I used it for? I used it to put out the fire. So that was $1. I used wine to put out the fire. So, well, I thought I was getting such a great deal. It turned out to be kind of expensive for what it did with it. Anyway, let's take a break now, and then we'll finish this up. What's wrong with this particular Lewis structure?
Boron doesn't have the complete octet.
Yeah, boron doesn't have an octet. You see, boron only has 2, 4, 6. One way to make an octet is to take a lone pair and create a double bond. But when we do that, it changes the formal charges. Right now, the formal charges are all 0. And the chlorine has 7 electrons, formal charge. It's supposed to have 7 electrons. Boron has 3 electrons. It's supposed to have 3 electrons. So all the formal charges are 0. If I make a double bond, then that means chlorine's going to go positive and boron's going to go negative because chlorine's essentially donating an electron to boron. Do you think chlorine wants to donate an electron to boron? No. Chlorine's highly electronegative. It's a powerful oxidizer, so it doesn't do that. And so what's going to happen is this is going to be stuck at less than an octet, and this is going to be the same structure. This is the same thing here, number 6. Problem is beryllium doesn't have an octet. But in order to make an octet, we'd have to form a double bond with this fluorine and a double bond with that fluorine. And that means each of those fluorines are donating an electron to beryllium. It's going to make fluorines positive and beryllium negative 2. Do you think that's going to happen? No. And so this is less than an octet. It's going to stay that way. And this one. So both 1 and 6 are fine as it is. How about number 2? Does that look good to you? What's wrong with number 2?
The oxygen on the far right is so full.
Yeah, this doesn't have an octet. But maybe the electron count is wrong. Let's take a look. Nitrogen's 5. 3 times 6 is 18. That gives us 23 plus another electron, 24 electrons. So do we have 24 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We don't have 24 electrons. We only have 20 electrons in the structure, do you see? So we have 2 more lone pairs. So if we put 2 lone pairs on that oxygen, does it fix it?
Yeah.
It fixes it in terms of octet, but does that structure look good to you, or does it look... So I add the 2 lone pairs of oxygen, that fixes the octet on this oxygen, but it doesn't fix the structure. There's something else wrong with the structure. What else is wrong?
Would oxygen double bond with itself, or?
Yeah, oxygen doesn't like to single bond to itself, but I'll tell you what's wrong with the structure is this.
Yes.
What's the formal charge on this nitrogen?
5.
Well, it's normally supposed to have 5. How many does it have in this?
7.
2, 4, 6, 7?
7.
Minus 2 formal charge. What's the formal charge on this oxygen?
Minus 1.
Minus 1. What's the formal charge of this oxygen in the middle?
Plus 2.
Plus 2. So we have minus 2, plus 2, minus 1, and 0 if we have 2 lone pairs on here. Does that look good?
No.
No. And so one way we can fix this is not put an oxygen in the center. Instead, we put the least electronegative element in the center, which would be nitrogen. So if we put nitrogen in the center, then we have no problem with that. And that would be nitrate ion. And so nitrate ion has this structure. Where This is okay. I mean, we're going to have formal charges, but oxygen is more electronegative than nitrogen. So nitrogen is going to lose, but nitrogen still has not cat, and so everything has not cat. It's not like you're going to have this. If you try to visualize what's happening here, this is -2, that's +2. So nitrogen took 2 electrons away from oxygen. That's not going to happen. Oxygen is more electronegative than nitrogen. And so this is nitrate here. We have 3 resonance forms that we can draw for this that are going to help stabilize this structure as well. Resonance forms help delocalize the electron density, electron quality structure. Can you name this? HClO3? Hydrochloric acid is HCl, but this is HClO3, which is not hydrochloric acid, it's chloric acid. This is chloric acid. Does this look like a good structure for chloric acid? No, it doesn't. Let's check the electron count. That's 1, 7 is 8, and 3 times 6 is 24, so it's 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. Is that 20? No, 18, sorry. 18 plus 8 is 24. So that's the right number of electrons. Everybody has an octet. Everybody has an octet except for hydrogen, which only needs a duet.
Doesn't hydrogen usually bond to oxygen instead of?
Yeah. Number one, the first clue is this is an acid. Acids have the hydrogen bonded to the most electronegative element. In this case, the most electronegative element is oxygen. And so the hydrogen shouldn't bond to the chlorine. The hydrogen should bond to the oxygen. And so chloric acid, the structure for that is going to look like this. And that would be, there are formal charges here, minus, and 1, 2, 3, 4, 5, plus 2. If it's 0, we don't have to write the bracket. The plus 2 minus 1 gives us 0. All the other formal charges are 0. How about number 4? How does number 4 look to you?
The center carbon doesn't even have enough.
Yeah, the center carbon doesn't even have an octet. It's not good. Maybe we miscounted the electrons. 3 carbons is 3 times 4 is 12, plus 6 hydrogens is plus 6 is 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That's the right number of electrons. How can we rearrange the structure to get carbon to have an octet? Is it possible?
Can I put a double bond on one of the carbons?
Okay. We'll make a double bond. So what I did was I took the lone pair and dropped it into the bond over here. Does that work?
And then put the hydrogen to the far left onto the middle one?
Okay. Put the hydrogen, which hydrogen?
On the far left.
This one? On the middle one? Okay. Okay. That looks good. Can I draw a resonance form for this? That is, I'll have the double bond here. Can I move the double bond over there?
No.
No, I can't do that without having to move the hydrogen. Resonance forms, we don't move atoms, we only move electrons. How about number 5? You know what this is called? HCN. Yeah, cyanide. It's called hydrogen cyanide or hydrocyanic acid. So if we look at hydrogen cyanide or hydrocyanic acid, does that look like a good structure for that?
No, the carbon doesn't have it.
Yeah. Carbon doesn't have an octet. So can we make the carbon have an octet? Yeah. We would just do what?
Triple bond?
Make a triple bond, right? Take a lone pair here and make a triple bond. If we do that, then that structure should be fine. So HC triple bond N lone pair. That would be hydrogen cyanide. Number 6 is okay. What about number 7? Does that look okay?
Yes.
Yes. That's good. This is an ether. It's a COC. Right? A COH is an alcohol. It's just that. This is called dimethyl ether. Those 2 methyls attached to the oxygen. How about number 8? Does that look okay? Looks like the octet rule is good. Or no, the octet rule is not good.
Yeah.
Yeah, carbon will never expand its octet. And so this carbon has 2, 4, 6, 8, 10 electrons. This exceeds the octet. Bromine's okay. How can I fix this structure? I need to remove this double bonding pair and give it to bromine. So if I take that double bond off there and make an extra lone pair, then I'll have 3 lone pairs and a single bond that's an octet, and then 4 single bonds for carbon that's an octet.
Yeah.
How about for carbon monoxide? Does this look like a good structure? No, there's no octet. Yeah. But here, carbon's 4, oxygen 6 is 10 electrons, so 2, 4, 6. We're missing 4. So we'll put a lone pair on carbon, lone pair on oxygen. Then that works. How about this one?
Hydrogen can't.
Hydrogen is not going to do this.
That's
Yeah. Oxygen, single bonds are unstable. So we try to avoid it, but sometimes you can't avoid it. In this case, we can't avoid it. We're going to have an oxygen single bond. Carbon loves to bond to itself, but oxygen doesn't. And so this is an unstable bond. This is called a peroxide bond. Peroxide bonds are easy to break. And so this would be hydrogen peroxide. Yeah. So avoid forming peroxide bonds unless absolutely necessary. In this case, it's absolutely necessary. No choice. Some of these are hard. What would you describe this shape as? To me, that looks either trigonal pyramidal or trigonal planar. What do you think? Trigonal pyramidal or trigonal planar? Yeah, maybe probably pyramidal. This looks linear. This looks trigonal planar. This is bent. This one's going to be bent at 109 because it's oxygen. It's water. This one is tetrahedral.
Bent.
This one's bent. But is this one bent at 109 or bent at 120? Can you tell? It depends on what this blue one is. If this blue one is sulfur, and this is sulfur dioxide is what they put in wines, the antioxidant. Then it's bent at one angle. If this is nitrogen is oftentimes blue. This would be nitrogen dioxide, which would be at a different angle. But we have to, in order to tell if it's bent at 109 or bent at 120, is we have to have a Lewis structure. And so let's make that nitrogen, and we have nitrogen dioxide. Nitrogen dioxide is kind of weird because it's an odd number species. Nitrogen has 5 electrons, and then we have 2 oxygens. There's 12 electrons. So altogether, we're going to have 17 electrons. Now, if it's going to boil down to oxygen versus nitrogen getting the octet, oxygen is going to win. Oxygen will win. So this oxygen has an octet, that oxygen has an octet. That leaves nitrogen the loser. Nitrogen is not going to have an octet. But maybe I can improve the situation. Would this be an improvement here? Let me do this. I'm going to make 2 double bonds. So we'll have oxygen, nitrogen double bond, and then nitrogen, oxygen double bond. And so now I have 2 double bonds. Is that better or worse than this structure here? Well, let's take a look at the formal charges. If I look at the formal charge here, it's a 1, 2, 3, 4. It's +1. It's missing. If I look at the formal charge here, 1, 2, 3, 4, 5, 6, 7, that's -1. The formal charge is plus and minus. Usually we don't write the 1 unless it's an oxidation state, so plus and minus. What are the formal charges over here? Formal charges 1, 2, 3, 4, 5, 6. How many is oxygen supposed to have? 6. 0. How about this? Nitrogen has 1, 2, 3, 4, 5. It's supposed to have 0. And then over here, 1, 2, 0. This has got to be better. All the formal charges are 0, right? And both of them violate the octet rule. And so which one do you prefer? The right one or the left one? The left one? The left one, yeah. The right one is no good. Because it goes over an octet. You can't go over an octet. So the right one's bad. It's good. We're going to have to live with the left one, but there's going to be another resonance form for this, in which we have the double bond over here, single bond over there. So that's going to help stabilize this, even though we have the formal charges on that. And so is that bent at 109 or is that bent at 120? How many groups of electrons are on nitrogen? 3 groups. This one is a single electron or radical group, a single bond group, and a double bond group. 3 groups means it's going to be bent at 120. So this is bent at 120. See how good we are at estimating bond angles. Bond angle A, the HCC bond angle, estimate that for me. Or just tell me the ideal angle. HCC. Angle A is ideally 120. There are 3 groups, single bond, double bond. 3 groups is trigonal planar. Trigonal planar is 120. Angle D. Here. Ideal angle would be 120 also. 3 groups, single, double, single. 3 groups, 120. These angle A and angle D are going to be distorted. The double bond is going to take up more space, so this is going to be distorted to about 122. This is going to be distorted to about 122. B. Is that bent at 120 or is that bent at 109? 109. It's 4 groups, 2 lone pairs, 2 single bonds. I don't like this. If it's bent like this, then the 2 lone pairs should be up here. 1 wedge, 1 dash. We don't have, this is weird geometry here. But this is bent at 109. Angle C. What's the angle for that?
109.
109. That's a tetrahedral. Let's take a look at this is aspirin, by the way. Aspirin acetylsalicylic acid. So this is the CO OH group here of the acid. This group here is called the ester group. It's a COC double bond. We go to lactic acid, angle A, ideal. Angle B, ideal. 109. Angle C, ideal. 120. Now distortions, angle A, do you expect any distortion? Angle B, do you expect distortion? Yes. What do you expect this to be distorted to? 105. Angle C, do you expect distortion? What do you expect this to be distorted to? 118. Okay, 118 is a good guess, but it's going to be pushing here, and it has to add up to 360, so it gets distorted to 116. 2 degrees from this side, 2 degrees from that side compresses this by 4 degrees. So the three angles have to add up to 360. More with this cinnamaldehyde. Angle A, ideal. B, C, is up here. These are the same.
122.
Ideal. Okay, how about distorted? A,
122.
122. B, 122. C,
Also.
also 122. Yeah. That would be the distorted. Amphetamine. This is a mean, but this trigonal pyramidal is tilted on its side, so we're looking at the base this way. The top of the pyramid is pointed away from us. And so they just oriented it differently. They oriented it so they can get the zigzag pattern like this, but as many atoms in the plane as possible. Yeah. These are all trigonal planar carbons here, so they're flat. And they flatten out the rest of the molecule here. That doesn't mean this can't rotate. This can rotate around. But what's angle A? Angle B? It's easier to see here than here, but angle B would be 109. Angle C? 109. Okay. Any distortions to A? Yeah, this should be around what? Guessing around 122. B, any distortions to B? No. C? Yes. C should be, ideal is 109, distorted is going to be 107. So this angle should be about 107 on the legs of the. All right, let's take a look at this. We're not going to look at what's the electron geometry for this? Tetrahedral and the molecular geometry. This is going to be bent at 109 or bent at 120? 109. So this is tetrahedral electron geometry, bent 109 molecular geometry. Okay, what's the electron geometry here? Linear. Molecular geometry? Linear. Angle? No distortions here. What about this one? What's the electron geometry? Tetrahedral, so it's 109. And the molecular geometry? Trigonal pyramidal. This one? Trigonal planar. Angle? 120. And the molecular geometry? Trigonal planar. This one,
Tetrahedral.
tetrahedral. Angle, 90 degrees?
No.
No, angle is
109.
109. And molecular geometry? Tetrahedral. Okay, I'm just going to ask you the molecular geometry and the angle. What's the molecular geometry and angle of this? Tetrahedral, 109. Any distortions? No. This one's simple too, so let's do this one. What's the molecular geometry and the angle? Tetrahedral and 109. What do you suspect the molecular geometry for this is? Is this linear molecular geometry? No. Okay, tetrahedral would be the electron geometry, and that's correct. This would be tetrahedral electron geometry, but its molecular geometry will be, it won't be linear, it will be what? It's going to be is it bent? It's bent. So this is tetrahedral electron geometry, which sets the angle. The angle is going to be 109, which means the molecule is going to be bent. Whereas this one is not bent. This is linear because the electron geometry is linear and the molecular geometry is linear and the angle is 180. What's the molecular geometry and the angle for this one? Ideal angle. Using tetrahedral? Tetrahedral is the correct electron geometry, but what is the molecular geometry? Trigonal pyramidal. The ideal angle? 109. The distorted angle? 107. So this is trigonal pyramidal. This one is trigonal planar angle? 120. So normally we're asked what the molecular geometry is. You know, people want to know the molecular geometry. They don't really care about the electron geometry. But the electron geometry is going to dictate what the molecular geometry is. And so we need to know the electron geometry and then the molecular geometry. And so some people might classify both these as linear, but they aren't. And some people might classify both these as trigonal planar, but they aren't. That's because they have different. But anyway, we'll take a look at some more of these problems next time. Here. And since we're out of time today.